So, hey everyone, thanks for joining. This presentation is going to be about some research I performed a couple of months ago about the Linux kernel and stack exploitation. So we're talking about some pretty common stuff, but it turned out not to be that straightforward. So we'll see what I'm talking about shortly. So a couple words about me. I'm Davide. I do offensive security at Betrusted, which is a new company we just founded. I'm also an instructor for malware analysis and pen testing at different Italian universities. And I also hold an MSc in IT security and a couple other certifications I won't go over. I'd like to define myself as a zero-day enjoyer, especially recently, since I had a lot of pleasure expanding my knowledge, reading about write-ups and articles about all different kinds of Linux vulnerabilities and zero days. So the agenda for today, we will be going over some trends, some history about Linux zero days, talking about why this presentation I think is relevant, and by grouping the vulnerabilities that came out in the last 10 years by class and by component. Then we will go over the analysis of some recent kernel vulns, trying to find out why they're limited and where those limitations come from. So we'll be talking about mitigation, of course, the anatomy of a successful Stack Overflow. That's just how to overcome those difficulties. So how to bypass controls and how to leave the interrupt context, which is a hot topic recently. So we'll be talking about that more deeply later. And finally, how to mitigate the risk in our own kernels. Because yes, we're black hats, whatnot, but we also like to feel safe using our Linux kernel. So I got some pie charts from you. On the left, we have Linux 3.x and 4.x, so about 10, 12 years ago. And on the right, 5.x and 6.x, pretty much the most recent versions. And I tried to categorize them into 4 different types of classes. Of course, we know that this definition is not practical because they might overlap. A particular race condition might trigger HITB overflows in some specific cases. But it's just to give the idea that stack overflows have been pretty much killed nowadays, and we're trying to bring them back. So the source, for those of you asking, that's just a lot of JQ queries on the NVD database, which collects all the CVEs and CWEs for all those Linux versions. I just grabbed for those security classes and tried to come up with some statistics. Same thing, but by component, we see 3 main protagonists. First one is netfilter, second one KVM, and then we have BPF. Over the years, BPF has been significantly hardened, especially for its consequences and its impact on the security point of view, since now it cannot be used anymore for privilege escalation, but only for particular like SE Linux bypasses. But KVM, on the other hand, has been used to escape from VMs, and netfilter has been around, has always been around. So this is the safe haven that I found to look for vulnerabilities. Let's have a look at some recent kernel vulns and try to understand where they come from and why they're so important. Now, I couldn't find many write-ups about kernel vulns. The first one I got to check out was this one. It got CV 0435. It's also been presented by last year at Hack in the Box, so I won't be going deeply into it, but it's basically a Stack Overflow in TIPC. It's different nodes that exchange domain informations and domain records. And the most recent one from each peer is stored on the stack for caching purposes, and their save function does not correctly check the boundaries of the domain members. So you can, in the payload, specify a higher numbers of members than it's in the header, and it will think that it has less domains than less peers than it actually has. So you can actually trigger an 800 byte overrun on the stack. Looks like a great primitive. 800 bytes is more than enough for doing anything, at least in the 90s, stack smashing and whatnot. This is the basic topology of the stack. We have the vulnerable structure, and we can go forward and overwrite everything. And the condition after the overflow is the following. Of course, not good. We overwrote the stack canary and also the subsequent kernel stacks that are 2 pages long. So between each pair of pages, there is a guard page. And if we try to overwrite the guard page that sits in between each stack frame, we run into some stock guard problems. So we have to find another way. Good thing is that this exploit is remotely triggerable, so it does lead to RC. It can overwrite easily the saved RIP, and we have a powerful primitive with 800 bytes overrun. But is it really that strong, or are we looking for something more right now? Well, it turns out we cannot easily corrupt those frames. So where can we pivot to do other stuff like privilege escalation and, I don't know, syscall hooking? Can we call set memory X to make our stack executable? Well, of course, that's a great idea. But the fact is that we need to manually disable some security mitigations like the stack protector, which is just a stack canary, and the config randomize base and image. That are basically KASLR, but with different scopes. Like, I think base image stands for randomizing the whole kernel image, and base is for the vmalloc base, and the vmem map base, and the page offset base. So 3 different randomizations in one security measure. Secondly, we don't know where we are. We don't know where to jump to it. We don't know what to write inside the stack canary. So we have to think about, is there something else we have to worry about? Well, except for KASLR and stuff, well, KPTI was introduced in software in 2017, one of the first mitigations, and it separates page tables between userland and kernel land. Basically, you have minor visibility from userland of the kernel pages. You only have what's necessary to switch to the kernel context and nothing else. Then you have SMEP and SMAP that go further than KPTI. They are implemented in some hardware, x86, 64, for example, and they prevent you from writing, reading, and executing from kernel land to userland. So if you're compromised some kernel pointers or other stuff, you still cannot store your payload into userland. Then we have FG-KASLR 2020. It's a more granular KASLR, but actually I couldn't find any good example of it in the wild in appliances. So I think it's not widely implemented and it has still room to grow. Basically, it splits the big text image into sections. So you have like text 1, text 2, etc. That correspond to a single function. And at load time, they get shuffled around in the kernel image space. And of course, the relocation has to account for that. Otherwise, the symbols won't be able to be found. Then we have the most annoying one, Per-syscall stack offset randomization. That is our iterative KASLR. Basically, at every syscall exit, the stack will shift of a random amount. Let's look at something that actually works as a full chain. So that starts from 0 and ends up as our privilege escalation as root. KASLR, we know it. We just need a leak, nothing new. As for KPTI, there are different measures. So we can just restore userland page tables with the so-called trampoline. We will see more about it later. Or use user mode helpers. They stay true to their name since they help you get code execution in user mode from kernel land. So yeah, they help the user in that. Two examples are core pattern and mode probe path, the second one being the most relevant. SMAP and SMAP, we just never worry about userland. We just keep everything in kernel land and do a ROP chain there. Of course, we have to find a way to do it. FG-KASLR, even if you found it around, you still shouldn't worry about it because it just uses a pretty restricted amount of symbols just from the text plus that offset of symbols. So the other stuff is still not randomized by it. Or you can use leaks from the symbol table that contains the offset from the symbol itself to the actual symbol in the kernel. So you can, with a particular leak, you can then recalculate all the other symbols that have been randomized. And the data section is still at a fixed offset, so you can use user mode helpers once again. As for the offset randomization, you can rely on one-shot exploits, which we will see later, or start from the interrupt context, where this has no effect as of right now. Let's talk about pretty much the first write-up I found about the complete exploit chain. It was in the Nftables subsystem, which is considered a newer version of IP tables. It consists of an OB read and write on the stack. You can basically use an expression, an NFT expression, to read and write up to a certain amount of bytes from the vulnerable structure, which is NFT regs. And based on the type of chain that you choose, input chain or output chain, you will end up in a particular context of execution. For the input chain is the interrupt context, and for the output chain is the syscall context. So you can fiddle around with that and find the one that suits you the most. The info leak, for the info leak, you can just read out of bounds whatever you find. I hope that some kind of text addresses and canaries end up in the leaked memory. As you can see from here, in the blue rectangle, we have an instruction address, and in the red one, a stack canary ending with the null byte. As for code execution, the goal is always the same. We want to overwrite the RIP in a stealth way to jump somewhere else. And so we need to find a particular frame that we can OB write to in order to only ever overwrite the return address by skipping the canary, which sits in between the local vars and the actual return address. So yeah, the constraint, we do not have to touch any canary. You can fiddle with input-output hooks. As I mentioned before, you can use UDP, TCP/IP packets and find the stack frame that's most suitable. And you end up with this condition where you can actually start from the OB write offset and write your ROP chain starting from it. A different approach for the same problem is one vulnerability I came up with a couple months ago. It's a pretty simple stack overflow. It has to account for the double VLAN tag length inside an SKB packet that you receive that has to be forwarded to the appropriate interface. And here we're trying to align it to the second VLAN tag, but you should decrease the offset and not increase it. So this ends up doing the opposite, and then in mem copies, it overflows to, it's a basic integer overflow, and then you can mem copy up to 256 bytes to the destination registers. What are these registers? Just a basic data structure. You can think of it as an array that the user can control in some way. So if you can write kernel stuff to the registers, you can then read them and obtain a complete info leak, which is what I did. Yeah, so 251 actually byte overrun because the first register you don't really control it from the reg structure in the NFT do chain function of the Nftable component. This is not enough for stack smashing, even if you wanted to. Of course, that's not a practical solution, but can always be considered. This is the layout of the registers. We start from register 0 up to register 15. And if you want to obtain an info leak, we can just trigger the volume from reg 0 and overwrite up to the reg 15. And as before, just look for anything that we can be happy about. And yes, we find some leaks. So that way we can defeat KASLR at least. But can we also defeat per system call KASLR? We will see. As for memory corruption, well, corrupting is always easy. Code execution a bit less. Well, before we started from rec 0, now we start from rec 15 with the overwrite, and whatever comes next, well, not very lucky for it, because it will be overwritten with our random content from the mem copy. And basically if you do that, you end up with a protection fault. So we did overwrite something that we shouldn't have. And a second look revealed a particular path to overwriting a function pointer starting from a structure that controls the different steps of the execution of the NFT rules. So we end up controlling the expression pointer, which is a parameter of this function, and it will be like immediately evolved without any check. So if we can overwrite the expression pointer, we then have basically a free jump instruction that we can exploit. What are the issues with this approach? Well, we need some space for our payload. We see the registers, but they of course are not as large as we want them to be. And we do not want to touch userland, nor read to user, please. NFT register only offer indeed 64 bytes of storage, which is not enough for the gadgets and the register that we want to push and then pop. So that's the problem. We also want to push those values. Controlling the expression pointer is of course space consuming because we have to pass from an intermediary structure. It's not a straightforward overwriting of the function pointer. We have to do some intermediary steps, and that requires space. You can check out the whole write-up if you're interested. So what is the solution? The said mem copy also includes our payload in its source. So we can actually duplicate our content at the beginning of the exploitation. So we first set up the NFT registers with our stack pivot. Then we trigger the vuln, and the mem copy will duplicate our content elsewhere, in the jump stack in particular. But it's still pretty much controlled by the user, so we also have another space that we can control. Then we refill the NFT register with other data. And in this case, it will be the raw payload that will be used to elevate our privileges. We call it stage 2. Then we redirect execution like we saw before to stage 1, which will pivot to stage 2, and we're happy. We call our user mode helpers, we override the mode probe path variable, and then we can execute code. But we're not done because we also had to exit correctly, otherwise we will just panic. In particular, we clobbered some functions, so we need to leave them without panicking. Well, we have the k-stack offset that does not apply to the interrupt context, as we said before, so we're pretty happy with that. But stack pivoting is, of course, pretty easy with low offsets, because you can look for every function in the kernel or at a certain moment at the epilogue. See, each function will have a different number of callee saved registers. So you have basically 3 primitives for pivoting the stack. If a certain function pops 10 registers and then the RBP and then rets, you can calculate the exact offset that will be that you will be increasing the RSP off, and then KASLR leaks stay valid until reboot, because of course k-stack offset is not influencing our payload. Some strategies that have been used before to leave the interrupt context. There is this very long symbol, swap.js, restore regs, and return to user mode. In a few words, what it does is just it swaps the GS register with the user line 1, so it basically does the context switch, and then it calls the iRetQ instruction that actually returns to userland and restores the stack pointer, the instruction pointer, and the stack segment, and so on. We can ignore deadlocks if you're fast enough. Now, I had some problems in the beginning, but by choosing the right function to return to, you can actually prevent deadlocks from hanging and just kill the function before the problem is detected. So you just kill the interface. We noticed that the soft interrupt, the syscall stack, which is what we want to return to, is restored inside a function called doSoftIRQ, which is inside our stack frame. So we can choose the function that we want between the last one we clobbered and this one. And we should be good, unless some racy stuff happens. In my case, I decided to pick the nfhookslow function and return to it, and it turned out to be sufficient. So how can we mitigate the risk inside our kernels? Now we have been working with the Linux Foundation to come up with more stable solutions. Of course, we have workarounds. You can config the user mode helper as a static variable. That means you cannot overwrite the mode probe symbol anymore. It will be ignored, and only the one used at config time will be used. Or they already thought about it, at least on some architectures. We can have in-kernel pointer authentication, like the one they have on ARM v8.3, that is being merged into the main line since Linux 5.7, and it allocates a couple bits for the signature of each pointer, so we cannot use the ROP chain to jump to arbitrary location because each pointer will be validated. And we might think about something more creative, like the Per-softirq kernel stack randomization, which is what I started working on. So what does the layout look like when we're executing our code? We're in userland, with the RSP is pointing to the userland stack. Then we invoke a syscall, and we skip to the kernel stack of the current thread. On entering, you already have the kstack offset that has been calculated in the previous syscall exit. So this is not the fresh one, it's one that's been used before. So we're safe here. But then when we do the doIRQ function on the receive function of the NIC card, we enter the hard interrupt stack, which is a Per-CPU variable. And finally, it registers a soft interrupt to be run by the kernel thread that does all the soft interrupts. We enter the soft interrupt stack, and of course, here we do not have any randomization. The address at which we end up is always the same, given the same CPU. So if we're not doing multi-threading on different CPUs. And how can we mitigate this situation? How can we improve this situation? Well, we can, of course, just add another arbitrary offset here, but we cannot reuse the same that we use for the kernel stack, although that will be the most common solution, because then on the next syscall, you will have the same offset, and so a leak in a syscall context might also leak the offset in the soft interrupt stack, which will not work. So let's put it all together. In my opinion, Stack Overflows, especially in the networking subsystem, can be considered powerful and deserve another look, because developers still trust CupNetAdmin based on the capabilities model implemented inside Linux, and so they feel more safe writing code that is protected by the capabilities. Furthermore, the kstack offset doesn't work in softirq, so we need to find a solution for that, because the leaks are usable until reboot. And as we saw before, those kind of vulnerabilities can easily lead to remote code execution if not treated properly. Thank you. I don't have any question yet.